Hello, welcome to my talk on why some Reynolds numbers are so difficult to calculate. In this talk, we will first see the definition of the Reynolds number and the importance of the characteristic length and velocity in calculating the Reynolds number. Superficially, the characteristic length and velocity are very simple, but for some practical applications, determining the characteristic length and velocity might not be an easy task. In this talk, we will see the very first Reynolds number and the most accepted Reynolds number, and then we will see the examples for Reynolds number with difficult characteristic lengths, as well as the examples for Reynolds numbers with the difficult characteristic velocities. In physical understanding, Reynolds number is an indicator of the ratio of the fluid inertial force over the viscous force. That is, the Reynolds number is defined as this ratio of the inertial force over the viscous force. And we have then the Reynolds number expression as this and this. Here, rho, mu, and nu are the fluid density, the fluid viscosity coefficient, and the fluid kinematic viscosity coefficient, respectively. In a strict definition of Reynolds number, U and L are called the characteristic velocity and length. What are they? In the following examples, we will see the different characteristic lengths and velocities in different applications. The very first Reynolds number is the non-dimensional number, K number, used by Osborne Reynolds himself in 1895, and it was named as Reynolds number later in honor of Osborne Reynolds, who made the first exploration of the non-dimensional parameter on fluid states. Although Reynolds had also a similar non-dimensional expression in 1883, in which he used the radius of the pipe as the characteristic length. So in the definition of Reynolds number for the pipe, Reynolds himself used the capital K as the non-dimensional parameter given by this. And now we know this is actually the well-known Reynolds number given by this. Here we can see the characteristic length is the pipe diameter d, and the characteristic velocity is the mean velocity of the flow in the pipe u. If we examine this example, the other possible length is the pipe length, but the pipe length would have no actual effect on the fluid state if the flow is steady. And the other character velocity in this example would be the maximum velocity at the center line, like this or this. So we can see for the nominal flow, the maximum velocity at the center line is a well-defined parameter, see here. But for the turbulent flow, the maximum velocity at the center line would be confusing, see here. So that's why the Reynolds number for the pipe flow would be based on the pipe diameter and the mean velocity of the flow in the pipe. Osborne Reynolds gave the result for the nominal flow. The Reynolds number would be smaller than 1,900, and the turbulent flow would be the Reynolds number larger than 2,000. In the modern fluid mechanics, the critical Reynolds number for a pipe flow is 2,300, and the pipe flow would be turbulent when the Reynolds number is larger than 4,000. And between these two Reynolds numbers, the flow in the pipe would be transitional. In my understanding, the Reynolds number for 2D airfoil might be the most accepted Reynolds number definition. As the most used structure in fluid dynamics, the importance of airfoil performance is so critical in practical applications. For instance, as we have already talked about, the airfoil performance is very much dependent on the Reynolds number of the airfoils. The high Reynolds number airfoil and the low Reynolds number airfoils would have very different performance. How we can define the Reynolds number for a 2D airfoil so that the airfoil performance can be well linked with the Reynolds number of the airfoil. Generally, the well accepted for the 2D airfoil is given by this. Here we can see the characteristic length is the airfoil chord C. The characteristic velocity is the free stream velocity U infinite. Now if we look at the other options for the definition of the Reynolds number for a 2D airfoil, we can see here no ambiguous definition for the characteristic velocity U infinite. And it seems no ambiguous definition for the characteristic length for the airfoil chord. However, we may ask a question: can we take the airfoil thickness as the characteristic length? After all, the airfoil thickness could be an important parameter for the airfoil performance. The answer for this is no, because the airfoil thickness is not as important as the airfoil chord in terms of the airfoil performance. In a special case of a very thin airfoil, the definition of the characteristic length using the airfoil thickness would be mathematically wrong if the airfoil thickness is taken as zero, as we have seen in the thin airfoil theory. In the following slides, we will see some examples how we can calculate the characteristic length or the characteristic velocity. The first example is an airplane. How we can define the Reynolds number for an airplane. Obviously, an airplane is much more complicated than an airfoil. Indeed, we have some difficulties in defining its Reynolds number. First, we have no different choices for the characteristic velocity, but the flight speed U infinite. This velocity can be also regarded as the free stream velocity relatively to the airplane, if we assume the airplane is fixed in the air, like in the wind tunnel test. But the question is how we can choose the characteristic length for the airplane, since we have many different ways to define a length for an airplane. For instance, the plane length L, or the plane width W, or the diameter of the plane fuselage. But all these lengths cannot be used as the characteristic length, since these parameters would not represent the performance of an airplane. And we might have used the specific chord of the wing, see here, But if we look at the drawing, we can see C would vary along the span of the wing. So how we can define the parameter for a chord for the wing? In the application, the mean aerodynamic chord is defined as this C bar. Here, S is the surface area of the wing, and B is the span of the wing, and CY is the chord of the wing section at Y in the span of the wing. So use this characteristic length, we can define the Reynolds number for an aeroplane, given by this. The second example is for the Reynolds number for the wind tunnel test. Here, we take the annular low-speed pressurized wind tunnel as an example. The basic parameters for the wind tunnel are given in here. Test section 3.5 meter times 4.5 meter. The air free stream Mach number up to 0.36 in the working section. And the working pressure in the wind tunnel would be 3.85 bars. In this tunnel, a definition for the maximum Reynolds number for per unit length is 20 million. Here, the characteristic length L is 1 meter. So in defining the Reynolds number for the wind tunnel, we can see the characteristic velocity is well defined. It is the air flow velocity in the test section, U infinite. But we might have the difficulty to choose the characteristic length for the wind tunnel test, especially in the case of the test model is not decided. So there are two ways to present the Reynolds number for the wind tunnel. The first one is the maximum Reynolds number per unit length, and the second one would be based on the blockage ratio of 1%. So the characteristic length is calculated as this. And based on this characteristic length, we can draw a plot as this following the reference. So if we take an example, the Mach number is 0.2. In the conventional atmosphere, the Reynolds number for the model would be roughly 1.75 million. If we apply the pressure in the wind tunnel up to 3.85 bars, so we can have the Reynolds number roughly 6.8 million. The third example is the Reynolds number for a wind turbine. Here, we might have problems in both characteristic length and velocity. The first question is, what is the characteristic velocity? In this application, we might have different velocities. For instance, the air free stream speed, U infinite, not shown in this plot, it would be pointing into the screen. The rotational speed on the blade tip, omega r here, or the relative air speed at the given rotation r on the blade, calculated as U, given by this. We may also have the problem with the characteristic length for a wind turbine, whether we can use the turbine swept diameter equaling to r, or the turbine swept radius r, or the chord of the blade section at the given rotation. In reality, the Reynolds number for air turbine would be calculated as this for the airfoil at the given section on the blade. So the characteristic velocity is the relative airspeed at the given location, and the characteristic length is the airfoil chord at the given length on the blade. In this regard, the Reynolds number for an wind turbine is not a single value. It varies along the span of the turbine blade. From this plot following the reference, we can see there is a certain region along the blade span. The corresponding Reynolds number is almost a constant, for which corresponds to the maximum Reynolds number. Hence, we can take the maximum Reynolds number on the blade as the turbine Reynolds number. What happened for the Reynolds number at this region from about 30% to 85% of the blade? It is because the larger of R, the speed would be larger, but the blade chord would be smaller. See this plot. This is why the Reynolds number on the blade would have a region of a near constant Reynolds number. The last example in this talk is the Reynolds number for a moored floating structure on sea, such as an oscillating water column wave energy converter in this plot. It is moored using 3 catenary lines. So the float structure will move under the wave action. Our question is to study the floating structure motion in waves in a wave tank, how we can model it. Since in the modeling, we need to build a scale model for testing in the tank. We need to use the Reynolds number of the structure for sizing the model. See the reference here. And to decide in what situation the Reynolds number would be large enough. For instance, when the Reynolds number is larger than 100,000, then the viscous force would be much smaller than the inertial and the gravitational force of the fluid. And to model the physical model, use the fluid similitude only. To decide the Reynolds number, we first decide the characteristic length. It would be the diameter d for this truncated cylinder. The other length in this example might be the draft of the cylinder, but it is not so important as the diameter in terms of the structure motion under the wave action. Now we have a bigger question for the characteristic velocity for such a moored floating structure. Essentially, there is no free stream velocity in this example. The structure may move under the wave action, but the motion is the solution for the problem. It is not known a priori. Thus, we can't use it for calculating the Reynolds number. Can we use the wave velocity, but neither phase velocity nor group velocity is actual flow velocity? Following reference 1, the characteristic velocity can be taken as u equaling to omega a. Here, omega is the wave circular frequency, and a is the wave amplitude. By this definition, u is actually the maximum horizontal velocity of the fluid particles. As such,
The Reynolds number for the floating structure can be calculated using this formula.